Hello, welcome to the analytic number theory topics. In this video we are going to discuss the theorem 10.2 of chapter 10 in the textbook Analytic Number Theory written by Apostle. The theorem states that let the GCD of the two numbers a and m equal to 1, then a is a primitive root mod m if and only if the numbers a square, a cube, etc. a raised to the power 5m, a raised to 5m form a reduced residue system mod m. We can note that the numbers a square, a cube, etc. a raised to 5m form a reduced residue system mod m. If these numbers make a reduced form a reduced residue system mod m, and then the remainder is obtained when these numbers are divided by m are different. We get different remainders when we divide these numbers by when this set of numbers are divided by m. Okay, now we can discuss the proof of the theorem. Suppose a is a primitive root mod m. We consider the situation that a is a primitive root of mod m, then a raised to 5m. If a is a primitive root of mod m, then we know that using the definition of primitive root, a raised to 5m, a to the power of 5m is then congruent to 1 mod m. Then a raised to 5m is congruent to 1 mod m, and a known number f exists. And a known number f exists such that f is less than or equal to 5m and or less than 5m. There exists no number f which is less than or equal to 5m. Exactly saying that f less than 5m. See, when a number f is equal to 5m, then it's okay. That is possible. Equality is possible, but there does not exist. If there does not exist a number f which is less than 5m such that a raised to f is congruent to 1 mod m. Also let's imagine that the numbers a square, a cube, etc. a raised to 5m does not form a reduced residue system. Okay. Then there exists, if this is true, if the numbers does not form a reduced residue system mod m, then there exists, we can find two numbers I and j such that 1 less than or equal to I, where I and j cannot be equal, where 1 less than or equal to I, not equal to j, less than or equal to 5m, and also it's that satisfies a raised to I is congruent to r mod m, a raised to j is congruent to r mod m. That means we get the same remainders when the numbers a raised to I and a raised to j are divided by m. For convenience, for convenience of proving this, the theorem, let's assume that I is greater than j. We can, for convenience, we take that we can fix that I greater than j. Then a raised to I is congruent to using these two steps. Combining these two steps, we get that a raised to I is congruent to a raised to j mod m, because we get if this is true, we get same remainders when these numbers are divided by m. So you can write that a raised to I is congruent to a raised to j mod m. And that is we get a raised to I minus j. Therefore a raised to I minus j is congruent to 1 mod m. A raised to I minus j is congruent to 1 mod m. And that implies that I minus j is less than 5m. So we get a clear contradiction. So since why, how do we get that I minus j is less than phi m? It's because of this condition. We know that I is not equal to j, and both these numbers are less than or equal to phi m, so the difference must be less than phi m. Okay, since we have assumed that I is greater than j, so I minus j is less than phi m. Hence we get the contradiction. And this statement 1 contradicts the fact that a is a primitive root mod m. Okay, and because of because if a is a primitive root mod m, then there exists no number f less than phi m. See, then there cannot exist a number f which is less than phi m. Here the number phi m is used, but you cannot see that. So here this is f less than phi m. There does not exist a number f which is less than phi m. Okay, such that a raised to f is congruent to 1 mod m. So, but here it says that I minus j is a number which is less than phi m, and that satisfies the condition a raised to I minus j is congruent to 1 mod m. So these two statements, these two situations cannot go together. Since phi m is since a is the primitive root, so phi m is the least number. Phi m has that the property that it is the least number, satisfying the condition that a raised to phi m is congruent to 1 mod m. Next, conversely, we want to prove the converse part. Suppose that the numbers a square etc. to a raised to phi m make a reduced residue system mod m. Just imagine now we just imagine that there exists f a quantity f or a number f which is less than phi m, such that a raised to f is congruent to 1 mod m. Actually we want to show that a is a primitive root. We want to show that a is a primitive root mod m. Actually we want to show, for that we need to show that there does not exist a number which is less than phi m, such that a raised to that number, a raised to a to the power of that number is congruent to 1 mod m. So but let's just imagine that there exists a number f which is less than phi m and satisfies a raised to f is congruent to 1 mod m. Then we can also take that a is congruent to a mod m. We know that always this is true, a is congruent to a mod m. Then by multiplying this quantity by these two can be multiplied, then we get a raised to f into a is congruent to a, because here 1, so 1 into a raised to f into a is congruent to 1 into a mod m. That is a raised to f plus 1 is congruent to a raised to 1 mod m. We get the fourth statement. Now 4 contradicts the accepted fact that, see, the statement 4 contradicts the accepted fact that a square, a cube, etc. a raised to phi m make a reduced residue system mod m. It's because that shows that that shows that a raised to, see, what does it mean? It means that a has, when a is divided by m, we get a remainder, the same remainder we get when a raised to f plus 1 is divided by m. So the meaning of the statement number 4 is that a and a raised to f plus 1 give us same remainders. They give a same remainder when we divide these numbers by m. So that means the system a square etc. a cube etc. a raised to phi m does not make a reduced residue system. These numbers cannot make a reduced residue system mod m. So thus we get that contradiction. So since we get that contradiction, actually this is contradicted. It does not make actually we have proved that the numbers a square, a cube etc. a raised to phi m they make a reduced residue system mod m. We have proved that. So knowing that, you can say that we get the contradiction. It's because by following the steps in the conveys part of the proof, we have arrived at the conclusion. We have arrived at the conclusion that, or we have derived the conclusion that a square, a cube, etc. a raised to phi m does not make a reduced residue system mod m. That means they are contradictory, and the statement that means our conclusion contradicts the accepted fact, which was actually proved. That accepted fact is that the numbers make a reduced residue system. So something that we have previously taken is wrong, and that is what must be then wrong, and then we have to correct that. We suppose that conversely we suppose that a etc. make a reduced residue system mode, and just okay, then we have accepted that. Here we have accepted that a square etc. a raised to phi m make a reduced system mode, and then we want to show that. See here, this is the statement that we have very carelessly taken, what was about which we were not sure. So we just imagine that this is that statement that we want to correct. Actually, this was accepted as true. This statement, we are not sure about this statement, so we can correct that. We just imagine that there exists a number f less than phi m. F is less than phi m, such that a raised to f is congruent to 1 mod m. Okay, and this is the wrong statement, so we have to correct this. That means there does not exist a number f less than phi m. There does not exist a number f less than phi m such that a raised to f is congruent to 1 mod m. Okay, and that means these numbers then make a reduced residue system mod m. Okay, thank you.